Hello and welcome back to Maths Tutorials. Today we're going to be talking about how you can find the volume of a solid of revolution. So last time we talked about finding the area between two curves, I believe. And so that and finding the area under one curve between, a curve and the x-axis are both going to kind of feed into this idea. So if we take a look at something like this, right? Well, something like this. And you have a curve, let's say like that, right? Actually, let's make it easier now. Like this, right? And you say, let's look at this area, right? We already know how to find that area, right? But now, actually, let's do that. So let's say this is A, this is B, this is f of x, right? This would be so the integral from A to B, f of x dx, right? So now what if we wanted to rotate this whole thing around the x-axis, right? So if you can imagine, right, going from that, we would then have something like this, right? And we would rotate. So this would come all the way around, right? So like this, kind of. Imagine this is perfectly mirrored. And then this would be like circles, right? So like that. And then, of course, every single point is getting rotated the whole 360 degrees. So if you could imagine, right, this is kind of like I was gonna make a reference that nobody would probably understand, but like the Abyss Watchers hats. Anyways, kind of like a pointed hat, right? And it's a 3D object now. So how could we find the volume of this, right? So you might think, okay, well, if we have, you know, a circle, well, if we have a circle, this is the radius, right? And a circle is pi r squared. So maybe, radius squared then multiplied by pi. Maybe, this whole area is the radius. Maybe this is a one-dimensional line. Maybe this is like a two-dimensional radius, going up a dimension on everything. So maybe this whole radius, or this whole thing right here is the radius, right? So maybe you square this and then multiply by pi. And this idea is wrong, but it's actually pretty close. Um, the only real difference is you actually have to square the function um, inside the integral. You don't square like the whole integral itself, right? You don't do this squared, you do inside, right? And so the idea with that is, well, let's take a look, right? Basically, what you're going to do is find the volume or, area as it goes to zero, but you're going to find the, volume slash area of each disk, of each, circle here. So like this whole thing, right? And then this smaller one, and this smaller one, right? And to do that, you're going to do pi r squared a bunch of times. So really the thing you're integrating is this whole pi r squared. So this pi r squared is the thing you're doing a whole bunch of times. Because remember, integrating basically is like doing something a whole bunch of times, but they're all, infinitely many times, but it's infinitely small, right? That's kind of the whole idea behind integrating. So you're going to do that to this whole formula, basically. So instead of, well, let's look at this, right? Oops, the radius for each individual place is going to be from here to here, right? That's the radius of this big circle, the middle circle here to here, right? And the small circle, of course, here to here. I don't know if you can see that, but you get the idea. So what is this radius? Well, obviously this radius is just f of, you know, x, right? It's just whatever number, right? So let's say this is 1 and this is like 10, right? F of 1 equals 10. And so this distance here is 10, and that becomes the radius. So the radius, wow, okay. The radius is just f of x at whatever point. So basically, we can say that this whole thing you can turn into, of course, still a to b, but it would be pi. Instead of r, we're going to go f of x squared dx, right? And this is kind of what I was talking about earlier, right? So now that we have it in this form, of course you can have the pi inside, but it's easier to just kind of move it outside. So really, this becomes pi a b and then f of x squared, right, dx. Um, and this is the formula. You might see it instead of f of x, you might see like r of x. I don't know what, maybe revolution, maybe radius, I don't know, but you might see, at least my textbook is writing it as this, um, big R of x, and then, oh, they have like this square. So that you might see it written this way, but it's the same general idea, right? So that is the volume of something like this, right, where you have the area from the curve down to the x-axis and you're just rotating, right? But what if it's a little bit more complicated, right? So let's cover two cases, right? Let's cover the case where um, you're in between two curves, right? So let's say, I'll just move all the way over. Let's say something like this, right? Let's cover this case first. So let's say, what would be a good thing to do here? Um, let's see, what would be a good example? Okay, the examples in this book kind of suck. Okay, well, let's just say, actually, yeah, let's keep it simple. Let's keep it simple. What if we have a line like this, right? And it's going to blow your mind. What if we also have a line like this, right? And let's say we don't want this whole thing. We only want the in between, and this is all going to get rotated, right? This will all get rotated. So you can imagine what we're going to have is, well, if we just had a rectangle get rotated, that would create a cylinder, right? You can think about, I don't know, maybe a door, and like if there was no wall, what kind of shape would it make if you could just turn all the way? It'd be a cylinder, right? Because it'd be something like this. So we're basically going to have, with this, we're going to have a cylinder, but with basically just a hole in the middle, another cylinder hole in the middle. So let's see if I can draw this cylinder, right? Yeah, good enough. And then another cylinder in the middle, basically, is what we are going to have. These probably should have been dotted lines, but you get the idea, right? Kind of like a toilet paper roll, right? Because it needs to go on the rack or whatever. So that's what this kind of thing is going to produce. Now, you might think, okay, so we have this, right? We have the pi a b uh, r x squared dx. So you might think, okay, well, hmm, what would you think here? I would say it's pretty obvious that you need to do something minus something, right? So let's say you have, call this upper one f of x and the lower one g of x, right? So you might think, okay, maybe you keep the pi, right? But maybe you go, let's see, f of x minus g of x. That seems like it could work, right? Because, in a way, this kind of distance becomes the new radius, kind of. I mean, maybe something like that would work. Sorry, maybe it's like this, f of x minus g of x squared dx. And like before, this idea is close, but not quite. So the problem here is, like I was kind of alluding to, this isn't really the radius, right? Because it's going to go a longer distance, right? Because you have this to worry about, and that's going to mean more area or more volume later on. So what you have to do instead is, well, you can imagine it as two separate things, right? So let's say you have the big one first, right? So you have the big one with no hole in the middle. Oh, and we already know how to find the area of that because it'd be the same as over here, right? Because this is basically, function down to x-axis with no holes. That's what this would be. So we know how to find that. But let's say we just subtracted that again, right? If we can find here to here, and we can find here to here, then we can just find this one and then subtract this one. And it would basically be the same. So we're kind of breaking it up into two parts that we already know. So instead of this, right, I'm going to put this in red. Instead of this, we can think about it as um, pi a b of f of x squared dx minus pi integral a b g of x squared minus dx. No, not minus dx. Okay, and so now you can kind of rearrange this a little bit to make it look better. You can, of course, factor out the pi, and then you just have the AB. Well, you can combine these into one integral, basically, by doing this. AB f of x squared minus g of x squared dx, right? Because, same variable here, so you can do this. And so this is then going to be basically our formula for a volume with a hole in the middle. Um, so this is pretty easy to remember, I would say, because I think if you see this, it is kind of obvious, or at least it should be pretty intuitive that you're going to have to do some subtraction. So the big question is it this or is it this? And I'm going to be honest, I think this has tripped up a lot of people in the past, probably including me. I think I've gotten tripped up by the distinction between these before as well. But if you just keep in mind that you're really doing two completely separate operations and then just rearranging them to make it look better by factoring out the pi or whatever, it's pretty easy to come up with that it has to be this one, right? Because this one, obviously it would create, f of x squared minus 2 fgx or f of x gx plus g. I mean, it'd be a mess. So this one really kind of keeps them separate like they should be. So that's how you do it with a whole. And of course, we chose a simple thing, but this could also work with something that looks stupid like this, and then like this, right? It could work with anything. Um, of course, as long as f of x is, I think it has to be f of x above g of x, of course. If they cross over at some point, then you could just I don't know, switch over and consider two separate things, and then this part you treat g of x as the higher one. Um, so I think there was another case that I wanted to look at. If I remember, you're right. So basically, what if you are going around a line that is not the x-axis? So this whole time we've been rotating around the x-axis, which is is y equals 0. But what if you wanted to do something like this, right? What if you had, I'm just gonna steal the thing from the book. What if you had kind of well, let's say you had a line at, what do they have? Y equals 1. Yeah. So let's say this is y equals 1, and you had kind of this parabola type shape, and you want to see this area rotated between or around this, right? So not rotated around this whole thing. So this one actually doesn't even have a hole. It looks like it would, but really, if you look at it from here straight to here, there's no hole, right? So what would you do? Well, we know, let me see. Oh, and the equation for this is, let's say this is f of x, which is 2 minus x squared. Um, I don't think that quite, I think it should be like this, but it doesn't really matter. Um, so, oh, yeah, hold up. Whatever, doesn't matter. So you basically want to create kind of a new equation that keeps this line of rotation in mind. So the book says by equating f of x and g of x, g of x, I think they're saying this is g of x, though y equals 1. Because in theory, you could rotate it around a line that's not the lower thing, right? Because this is the lower boundary for this region, and it's also the line we're rotating around. Okay, so to find the radius, subtract g of x from f of x, right? So f of x is, let's say, this all the way down to here, whereas, actually, let me do that in a different color. So f of x is from here to here, right? Whereas g of x is here to, and remember this is going down to the x-axis because this is like the actual value of fx. So like, let's say this is 1, that's the whole value from here to here by definition is the value. So uh, to find this segment right here, you have to do f of x minus g of x, right? This segment right here is f of x minus g of x. So that's going to be your radius, right? So what is f of x minus g of x? Well, that would be 2 minus x squared minus y equals 1. So that would be 1 minus x squared. And then you can use this as your radius, your big R, right? And then you would square it, integral pi dx, all that stuff you would do after that. So basically, it's another thing where it's just a matter of you have to subtract two things. All right, so I guess that does it for this topic. It's a pretty big topic. This is one of my longer videos in a while, but I would say this is pretty important, right? Whenever you're finding the volume of something, and this is, especially powerful because you can do it if there's a hole in it. You can do it, for every type of solid of revolution, right? Even if it's not around the x-axis. So next time, what are we going to cover? Let's see. What is the shell method? I have no idea. Uh, the shell method. Cylindrical shells. What does that mean? Yeah, I have no idea what's going on here. I'm not gonna lie to you. I'm looking at this in my textbook and I'm kind of lost as to how this is different. So we're gonna skip it. Um, right. So next time we are going to do this. This sounds important. Um, arc length and surfaces of revolution. Yep, that, revolution. Okay, so that'll be next time. So I assume that'll be kind of like you have a parabola. What is this actual distance, right, of this line? And, that's obviously a lot more complicated than saying what's this distance or, what's this distance or whatever. So yeah, we'll do that next time. Until then, I'll probably be a little bit late next week on my video. Well, maybe. We'll see. But anyways, see you next week.